I want to start with an object. The single most important object in artificial intelligence is not an algorithm or a dataset. It's a chip. And that chip was designed originally to do one thing: draw explosions in video games faster.
The graphics card. The thing teenagers buy to make their games look good.
The thing teenagers buy. Nobody at those companies, in the 90s, was thinking about artificial intelligence. They were thinking about how to paint 2 million pixels onto a screen 60 times a second. And it turns out the math for paint a screen full of pixels and the math for run a giant neural network are, at the bottom, the same shape. Both are mountains of small, identical, independent multiplications, all of which can happen at once.
So the gaming industry spent 3 decades and untold billions building a machine optimized for exactly that shape of math, for completely unrelated reasons. And then deep learning showed up and discovered its perfect engine was already sitting on the shelf, in the gaming aisle.
And this is not a cute footnote. This accident shaped which ideas in AI won and which ones died. It's why neural networks, an idea from the 1960s, sat in the wilderness for 50 years and then suddenly conquered everything around 2012. The idea didn't get better. The hardware finally arrived.
And the flip side is the unsettling part. If the available hardware decides which ideas win, then we're not necessarily running the best ideas. We're running the ideas that happen to fit the chip the gaming market built. There could be a better path to intelligence that simply lost a lottery it didn't know it was in.
So today, how a graphics chip accidentally became a brain, the bedroom experiment that lit the fuse, why the hardware you have secretly picks your ideas for you, and the wall the whole field is currently slamming into, which turns out not to be about thinking fast, but about moving data at all.
This is Breach Protocol. I'm Luna. I read the papers and find the threads between them, and this is the episode that sits underneath every other episode because all of them, the transformer, diffusion, the giant models, quietly assume the hardware that makes them possible. Today the hardware is the story.
I'm Vestra. I take the machinery apart, and today I mean that literally. We're going below the algorithms to the silicon they run on. Because there's a temptation to think of AI as pure ideas floating free of matter. It isn't. Every idea in this field is shaped, chosen, and limited by what the chips can actually do.
And the argument we're going to build is almost subversive. The usual story of AI progress is a parade of brilliant ideas. The story we'll tell is that a huge amount of it was hardware, that the ideas often sat around waiting, and what changed was the machine underneath them.
So the arc. First, the accident itself. Why a graphics chip is shaped so differently from a normal computer chip, and why that shape happens to be exactly what a neural network craves. Then the spark. A single result in 2012 run on 2 gaming cards that flipped the entire field overnight.
Then the deep idea that this wasn't luck so much as a lottery, and that the lottery keeps running. Why good ideas lose to mediocre ones that fit the hardware better, told through a wonderful essay that names the whole phenomenon.
And then the frontier, where it gets counterintuitive. Because today the thing throttling these models isn't how fast the chip can calculate. The chip is starving. It can think far faster than it can be fed data. The bottleneck moved, and the smartest recent work is all about feeding the beast, not speeding it up.
And we'll close on the stakes, which are enormous and not really technical at all. What it means that the entire future of this technology rests on a tiny number of companies and a single, fragile supply chain.
Start with the chip. Start with why drawing explosions and thinking turn out to be the same problem. So picture 2 kinds of chip. A normal computer processor, a CPU, is like a tiny team of geniuses, a handful of extremely powerful cores, each able to do complicated things one step after another very fast. It's built for tasks where step 2 depends on step 1, sequential brilliance.
And a graphics chip, a GPU, is the opposite personality.
Totally opposite. A GPU is a stadium full of school children. Thousands of simple little cores, none of them brilliant, none of them able to do anything fancy, but all of them doing their one small sum at the very same instant. It's useless for a long chain of dependent reasoning. It's miraculous when you have a million identical little sums that don't depend on each other.
Which is exactly drawing a screen. Every pixel's color can be worked out independently at the same moment. 2 million pixels, 2 million tiny identical jobs. Hand them to the stadium.
And here's the punchline that took the field years to fully appreciate. The core operation of a neural network, multiplying big grids of numbers, matrix multiplication, is also a pile of identical little multiply and adds with no dependency between them. It is mathematically almost the same workload as shading pixels. The neural network was secretly a graphics problem.
There's a contrast in the hardware lottery essay we'll get to that always stops me. Around 2012, one famous project needed something like 16,000 normal processor cores to learn to recognize cats. Within about a year, the same kind of result was being done with a couple of processors and a handful of GPUs. Same idea. The hardware was just finally the right shape, and the difference was orders of magnitude.
Now, there was a missing piece, because for a long time you could only make a GPU do graphics. To draw, basically. You couldn't easily tell it, hey, do my arbitrary math. The unlock was a software layer, NVIDIA's, called CUDA around 2007, that let programmers boss the stadium around for any computation they liked, not just pixels. That's the moment the graphics card quietly became a general-purpose parallel supercomputer that happened to be cheap because gamers were subsidizing it.
And that word, cheap, because gamers, matters more than it sounds. The gaming market poured in the volume that funded the research and development and drove the price down. AI researchers got to ride a hardware curve that someone else was paying for. They inherited a supercomputer built for entertainment.
So by around 2010, you had all the pieces sitting in the same room without anyone having planned it. A chip shaped like a neural network's dream, a software key to unlock it for general math, and a price held down by teenagers wanting better frame rates. The fuse was laid. It just needed someone to light it.
2012. There's a big annual contest for image recognition. Show the computer a photo. It says that's a leopard. For years, progress had been creeping along, everyone using carefully hand-engineered methods, all clustered around similar middling scores. And then a team from Toronto, Alex Krzyzewski, Ilya Sutskever, and Jeffrey Hinton, entered a deep neural network, and won. Not edged ahead. Won by a humiliating margin. Cut the error rate so dramatically the field basically stopped what it was doing.
And the thing people forget is how unglamorous the secret was. The network, we call it AlexNet, wasn't a totally new idea. Deep convolutional nets had been around. What was new was that they actually trained one this big, and the only reason they could is sitting right there in the paper, stated plainly. They implemented it on 2 graphics cards.
2 consumer gaming GPUs.
2 GTX 580s, 3 gigabytes of memory each. And the network was so big, it didn't even fit on one card, so they split it across the 2 and let them talk. This is essentially a bedroom setup. The paper flatly says the network size makes it too slow to train on normal processors, and that the GPU implementation is what made it feasible at all. The genius was real, but the genius was unlocked by gaming hardware.
And there's a line in that paper that I think is one of the most quietly prophetic sentences in the field. They more or less say, our results can be improved simply by waiting for faster GPUs and bigger datasets to become available. No new idea required, just more.
That sentence is the entire next decade. It's the scaling hypothesis, written in 2012 by people who'd just proven it once, and they were right. The years since have substantially been, take this, make the chips faster, make the data bigger, repeat. The transformers, the giant language models, all of it rode the curve that AlexNet pointed at.
So 2012 is the Big Bang, but notice what kind of Big Bang it was. It wasn't a conceptual breakthrough that needed new hardware built for it. It was an old-ish idea meeting hardware that already existed, for other reasons, and detonating. The match meta fuse that gaming had laid years earlier.
And once that detonation happened, the money flooded toward the chips. Suddenly, the graphics card company wasn't selling toys for gamers, it was selling the means of production for an entire new industry. The accident became a strategy. But it started as an accident, and that's the part the next idea forces us to take seriously. Because if the right hardware hadn't happened to exist, the best idea in the room might have lost anyway.
This is the idea that turns the episode from a fun history into something with teeth. It's an essay by Sarah Hooker, 2020, called The Hardware Lottery, and the thesis is this. A research idea often wins or loses not because it's better or worse, but because it happens to fit the hardware and software of its moment.
Not the best idea wins. The idea that matches the available machine wins. And the rest, however brilliant, sits in a drawer looking like a failure when really it just drew a bad ticket.
And the centerpiece example is the one we keep circling. Neural networks themselves. The core ideas, the math for training deep networks, the backpropagation algorithm, were worked out decades before the boom. 60s, 70s, 80s. The ideas were there, and they went basically nowhere for 30 plus years.
because the dominant hardware, normal sequential processors, was catastrophically bad at the one thing neural nets need, those massively parallel multiplications. On that hardware, neural nets looked slow, clumsy, and worse than the alternatives. So the field largely abandoned them, for a generation. The researchers who believed in them were, in the language of the essay, holding a winning idea and a losing ticket.
And Hooker has this brutal line, "Being too early is the same as being wrong." Which is heartbreaking if you think about the careers spent on the right idea at the wrong time. It didn't look right because the machine to run it didn't exist yet.
And then the gaming market built that machine for explosions, and overnight the losing ticket became the winning one. The idea didn't change. The hardware lottery just paid out, which should make you deeply humble about the current moment, because the logic cuts forward too.
That's the part that unsettles me. We've now built a colossal hardware and software ecosystem optimized specifically for today's neural networks. The chips, the data centers, the libraries, all assuming this exact style of computation, which means the next genuinely different idea, some other route to intelligence that doesn't look like a big pile of matrix multiplies, starts life the way neural nets did, too slow on the hardware we happen to have, looking like a failure.
Hooker gives the example of architectures that don't map cleanly onto current chips, and therefore run dreadfully and get abandoned, regardless of whether the idea has merit. We may be doing the exact thing the 1980s did, mistaking "doesn't fit our hardware" for "doesn't work." The lottery isn't a one-time event in the past. We're inside one right now, and we can't see which good ideas it's currently starving.
It reframes the whole triumphant story. We didn't necessarily find the best path to machine intelligence. We found the path that fit the chip the gaming industry happened to build. Those might be the same thing. Or we might be a whole civilization optimizing in a groove we fell into by accident.
Now the frontier, and it flips the whole intuition. For years the assumption was, AI is bottlenecked by compute. We need chips that can do more multiplications per second. And chip makers delivered, spectacularly. But somewhere along the way the bottleneck quietly moved, and most people didn't notice.
Move to where?
To moving the data. Here's the situation inside a modern GPU. The cores can now do arithmetic so fast that they spend most of their time idle, waiting for numbers to arrive. Because the chip has two kinds of memory, a big pool that's relatively slow and far away, and a tiny scratch pad right next to the cores that's blindingly fast. And the cores can only work on what's in the tiny scratch pad. So the whole game becomes shuttling data between the big slow pool and the little fast one.
So the cores are a world-class kitchen that can cook anything instantly, and the entire restaurant is bottlenecked by how fast the waiters can carry plates from the pantry.
That's exactly it, and it has a name, the memory wall. The compute got so fast that feeding it became the hard part. And the beautiful illustration of this is a 2022 paper, FlashAttention by Tridao and colleagues, and notice, the same Tridao from our Mamba episode. He keeps showing up exactly where hardware meets algorithm.
What does it do?
It takes attention, the transformer's core operation which we covered, and it does not change the math at all. Same exact result, not an approximation. What it changes is the choreography of data movement. The naive way computes that big attention table and writes the whole thing out to the slow faraway memory, then reads it all back. Enormous traffic across the slow link. FlashAttention restructures the computation so it works on small tiles entirely inside the fast scratch pad, and cleverly never writes the giant table to slow memory at all. It even throws away intermediate results and recomputes them later because, and this is the wild part, redoing the arithmetic is cheaper than the round trip to fetch it.
That's the detail that breaks your brain a little. It is faster to recompute a number than to go get the one you already calculated. That tells you how lopsided the situation is. Arithmetic is nearly free. Fetching is expensive.
And the payoff was huge. Far less memory used, much faster, and it's a big part of why models can handle long contexts now. But the lesson is bigger than the speed up. FlashAttention didn't outthink attention. It out-choreographed the hardware. The win came from respecting how the chip actually moves data. The algorithm bent itself to the silicon.
Which is the hardware lottery wearing work clothes. It's not just which ideas survive, it's that even our winning ideas get reshaped in their fine details to fit the machine. The transformer we run today is subtly molded by the memory hierarchy of a GPU. The chip isn't just executing our ideas, it's editing them. So let's land the plane on what all of this means, because it's not really a story about chips. It's a story about power in a few senses of the word.
Start with the one that follows straight from the episode, concentration. If AI is bottlenecked by a very specific kind of hardware, then whoever makes that hardware holds the whole field by the throat. And right now, essentially one company designs the dominant AI chips. Its software, that CUDA layer we mentioned, is the language the entire field is written in, which means even a competitor's better chip struggles because everyone's tools assume the incumbent. That's a moat measured in years.
And it goes one layer deeper than that, doesn't it? Because that company doesn't even make the chips.
It doesn't. The actual manufacturing of the most advanced chips happens at essentially one company in one place, using machines made by essentially one other company in another country. The supply chain for the brains of modern AI narrows, at its tip, to a handful of facilities on Earth. The most strategically important industry in the world rests on a pinhead. That's why you hear AI and geopolitics in the same breath now. The export controls, the fab subsidies. It's all about who gets the shape of sand that can think.
And then there's the intellectual stakes, the hardware lottery point, which I don't want to lose under the geopolitics. We should hold real humility about whether we're on the right path at all. The triumphant version says we discovered how to build intelligence. The honest version says we found one path that happened to fit the chip the gaming industry built, poured the wealth of nations into that single groove, and we genuinely do not know what better paths were starving of the hardware they'd need to prove themselves.
There's a famous argument in the field, the bitter lesson, that the methods which win are reliably the ones that best exploit raw computation, and that human cleverness mostly just gets in the way of scale. And if that's true, it's almost a prophecy that hardware is destiny. The best idea isn't the cleverest. It's the one that turns the most silicon into the most progress. Which means the future of intelligence is, to an uncomfortable degree, a function of a foundry's roadmap.
And maybe the quiet final irony, the thing this whole episode keeps circling, is that none of this was designed. No one set out to make the chip that would host machine intelligence. They set out to render water and smoke and muzzle flash convincingly, sold it to teenagers by the million, and accidentally built the substrate of the most consequential technology of our century.
The brain of the future was a byproduct of better video games. If that doesn't make you humble about how progress actually happens, accidents, lotteries, byproducts, I don't know what will.
So back all the way out, the whole episode is one inversion of the usual story. We tell ourselves AI advanced because we got smarter. A truer telling is that AI advanced because a chip built to draw video games turned out by accident to be shaped exactly like a neural network's dream. Thousands of tiny workers doing identical sums all at once.
And once you see that, the dominoes line up. Neural nets were a good idea stuck on the wrong hardware for 30 years. Too early, which looked the same as wrong. The gaming market built the right hardware for unrelated reasons. 2012 lit the fuse on 2 gaming cards. And ever since, the field has mostly been riding that hardware curve, even bending its best algorithms, like FlashAttention, to fit how the chip moves data. The silicon hasn't just run our ideas. It chose them, and it edits them.
And that should change how you hear every other thing we cover on this show. When we talk about the transformer, or diffusion, or some new model, there's an unspoken clause under all of it, and it happened to fit the GPU. The ideas that didn't fit, however good, you never heard of because they never got to run.
Which is why the hardware lottery is the humbling frame to carry. We are not standing at the obvious summit of intelligence. We're standing on the one peak our particular climbing equipment could reach. There may be higher peaks. We'd need different gear to even see them. And right now, the entire world is forging more of the same gear, faster.
And the stakes ride on a supply chain you could photograph from a single helicopter. The most important technology of the age, narrowing at its tip to a few buildings. That's not a comfortable place for a civilization to keep its brain.
But I'll end on the wonder, because it's genuine. There's something almost cosmically funny about it. The substrate of machine intelligence, the physical stuff now reshaping economies and politics and maybe minds, exists because a lot of people really wanted explosions to look better in their games. Progress doesn't arrive on the road we paved for it. It comes through the side door, wearing the wrong clothes, by accident.
That's the breach for today, and honestly, a fitting place to pause this run of episodes. The ideas we've spent all week marveling at all run on this one accidental machine. We close with a song. This one's called Built for Explosions. The Stadium of Children, the lottery, the brain that was a byproduct.
Stay in the black box. We'll see you next time.
I drive an industrial EBM with an arcade neon underglow gone dark. Thousands of tiny synth pulses spiral out like a stadium of voices, brooding female vocals, heavy analog bass, glitchy 8-bit ghosts, relentless and propulsive, cinematic, clean mix, fades out at the end. They carved you out of sand to paint the fire, muzzle flash and water, teenage desire. Nobody knew the math for smoke and flame. Nobody knew the math, the smoke and flame was the same math the mind would one day claim. Built for explosions, born to think, a stadium of children at the data's brink. Not the best idea, the one that fit the chip, won the lottery, nobody knew they'd skip. The right idea sat 30 years too soon, a winning ticket under a losing moon. Being early is the same as being wrong, till the gamers built the engine all along. Not the compute now, it's the carry, it's the hull. Genius kitchen, starving at the wall. Faster to forget and build it twice, then walk across the chip to pay the price. Built for explosions, born to think, whole world's brain on a single fragile link. Maybe higher mountains we will never climb, wrong equipment right